Okay, so let's say I have taken a few data set where I have children's intelligence score, right? In a scale of 1 to 150 or 200. So National Longitudinal Survey of Youth. So they have carried out certain standardized tests where 434 kids participated and these are their scores. What other independent variable what we have taken? Whether a mom has, whether their mother has high school graduate, right? So mom, high school graduate, yes means yes, no means no. That for a particular kid, let's say kid number 6, who has scored 98, his or her mother is not a high school graduate. Then what is the mother's IQ level, right? So that is a standardized score for all the mothers. They have gone through that standardized test and individual scores are given. Then whether mom or the mother is currently working or not, yes or no, right? And what is the age of the mother, right? 27, 27, 18, 25, like that. For all those 434 kids, all the information is available, right? Now what happens? By utilizing this data and I have created a regression of what? My, that person's, that kid's or that child's score, whatever in that test, national level test, whatever that kid has scored, that is my dependent variable. And what I'm assuming as independent variable is whether that person is high school graduate is not that kid, obviously his or her mother, what is mother's IQ level, whether mother is working or not, and age of the mother, right? So what I'm trying to find out, whether taking these variables or whether taking these four independent variables, mother's age, whether mother is working or not, mother's IQ, and whether mother is a high school graduate or not, can I predict the children's or the child's score, right? So if I ask you and I get this result, this is my output, whether using SAS, R, or whichever statistical package you have used. So I get an intercept, and these are the different variables, right, at different levels. I get this table, right? Now, if I want to interpret what do I mean by mom's IQ, how does it influence the child score, right? What I should look into or how to interpret that. Again, this is a repetition. This similar type of questions we have already discussed in previous classes. So I'll not spend much time just because just to revise before we get into the multicollinearity and outliers. So how do I interpret this mother's IQ when it says estimate is 0.56? How do I interpret that? What is the impact of this mother's IQ level on a child's whatever that is sorry her child's score in the nationalized test, standardized test? How will I interpret that?
So the impact of mother's IQ on the child's performance in the test is not by random. It has a significant impact because over here the probability value. So it is 0.00. So it shows that this is not happening by random or by chance. This is a significant impact. If the mother's IQ will increase or decrease, it will significantly impact the performance of the child in the test as well.
Correct. So always start with whatever the significance level, whether this variable is significant or not. So this p value, if I take my alpha as 0.05, 5%, right? So this should give me an idea that yes, this variable is a significant variable in predicting child's IQ. What is the impact? Impact may be less, right? So in this particular case, what is happening? For each unit increase in mother's IQ, kids IQ, kids score is improving by 0.56. But as Apurva told, initially you have to look into whether this variable is significant or not. Because here the probability or the level of significance it is showing 0, which is less than 5%. I can treat this variable as a very big significant variable, which is, so what do you mean by significant? If I carry out the same prediction for a different group of kids across America, right? It will give a similar result, it will give a similar type of estimate. So that is the meaning of significant. Because see, what do we mean by prediction? It is not that every time you will collect data. You have collected data and you have created a model. What I want to understand is that whether this model will be valid, will be working fine in different set of data, right? Once I have calculated, created this equation, whether any time I take mother's IQ, I can, with a like obviously 100% accuracy won't be there. With certain level of accuracy, I can predict kid score for a different set of data. So this level of significance talks about that. If we have remember what we discussed in BRM, so level of significance helps us to say that okay, if this is working, if I'm getting a good level of significance in my this sample, right, it is working actually for the population. This information remains valid for the population also, right? So similarly, let's say mother working, yes or no. How does that? How will I interpret that? IQ you have already discussed. Mother, mom work. Yes, it is showing as 2.54. How will I interpret this?
So since the value over here, the mother who is working, it is 0.28. So there is a less chance of the impact being significant, and more chance of it being random. So the mother working, if it is yes, then there is more chances that has a random effect on the performance of the child or the score that he has got in the national test.
Correct. So here, though I can say that. So that is first thing, like I said, a probability value you have to check. That gives you idea whether if I kind of execute this same sampling or similar type of data collection in a different area, right? Whether my estimate will remain same or not. Because here, if you see significance level is 0.28, which is greater than 5%. So that means the result or the estimate value might not be a replication, right? So that is first thing you have to look into. Second thing is that what we have discussed earlier, when you are comparing categorical variable, one variable which is not categorical variable, when we are kind of one categorical variable is taken as an independent variable. So one label of the categorical variable would have taken as the base label, right? The variable which is taken here is yes. So that means no, mother is not working has been taken as the base label reference. So if I want to interpret this for the sample data which I have collected, right? So all else being equal, kid whose moms work during the first 3 years of whatever their kid's life are estimated to score 2.54 points higher than those whose moms did not work. So keeping all other parameters same, age group, your whatever uh, other parameters, what else other parameters, IQ level, age group, high school graduate, keeping same. If I compare two mothers who one mother is working, other mother is not working, the mother who is working, her child would have a 2.54 points more score than the mother who is not working, the child's mother who is not working, right? But before you make this interpretation, you have to look into this. If you see age looks like 0.22, but if you see probability level of significance is very high, 0.51. So actually, for this sample data, you may use this equation. But when you are using the same equation to predict for other data, right, that estimate value will not be reliable. Same estimate value will not find same estimate value. But our focus is to get the to collect data once, create a model, and use that model multiple times. We are not in a position to collect data time and again, right? And that is where it is important to look into the p-value, because it gives a lot of explainability to the model, right? So that is one important aspect when you talk about the p-value. Other aspect, obviously, you know about the R-square, right? So already, if you like kind of in a model, whether any statistical package you use, already R square value is calculated. But let's say this information is given and now I am asking you to calculate R square. What will be the answer? So from this table, can you calculate R square value? If your ANOVA table of the regression model has been given, can I calculate my coefficient of determination or R square? Make a try. Remember what we discussed in R square. The R square is nothing but how much variation your model is able to explain. Explain whatever variation you can explain through that regression model divided by the total variation, right? So if this is one model which basically talks about how many female households and whether that household person is white, and we want to predict something, let's say the price of the house or something like that, and this model has been created. Anyone?
So is it 1 minus sum square?
Can you please repeat? 1 minus?
So the sum of square, like the second column.
Yes, you are in the right path. So how will you calculate that? So R square is nothing but my explained variation. How much my total variation is 480.25. Out of that, how much variation my model is able to explain? Female household explaining 132.57. White, the person whether white, black, or what other variable like kind of identification is there, that is only explaining 8.28 of the total variation of 480.25. So the variation which is explained by my model, I have to add these values divided by total, how much total variation is 480.25, right? So that will give me R square of 0.29. Other way to do it, 1 minus residual value, whatever 339.47 divided by 480.27. That also will give you the same result. If I just put that formula 1 minus sum of square errors, that is 339.47 divided by total sum of square, that is 480.25, then also you'll get a similar result. But if you go by the fundamental nature of what is R square, that is explained variation by the model divided by the total variation. Total variation or sum of square is 480.25. Explained variation is 132.57 plus 8.21. So that will give you a value of 0.29. So most of the times you do not calculate R square because model is calculating, but remember the fundamental, right? Because in the interview and all those things, they're going to ask you about what do you mean by R square, right? So how do you get or how do you calculate that value, right? So that is, I find out what is the sum of square which is explained by the model, right? So 132.57 plus 8.21 divided by the total variation. Clear? Any
Yes,
doubt
sir.
on this? Okay, so next obviously is the adjusted R square because as and when you keep increasing your independent variables, even there is no correlation. So that is what we have already discussed, something about those spurious regression, right? There is a very high correlation of ice cream sales and a suicide rate in a particular US state, right? Obviously, there is no logic behind a relationship between those two variables, right? And like that, there are a lot of, I think there is a site which talks about lot of types of different spurious regression. So the meaning is your R square value might be higher. R square value is showing a very good number, 0.9, 0.8. But that doesn't mean necessarily that there is a linkage between your independent and dependent variable, right? And as and when we keep increasing our independent variable, it will add to your Rsquare value, maybe by 2%, 1%, 0.5%, it will keep adding. So what might happen that unnecessary you will add independent variables, trying to fit a model which is not actually logically correct, right? So that is where whenever we talk about multiple regression, we do not look into R-square value. We look into something called adjusted R-square. So if you see this value is same, sum of square error divided by sum of square total. So this is the formula of R-square, 1 minus sum of square error divided by sum of square total. But what we are multiplying when we are calculating adjusted R-square is n minus 1, n minus p minus 1. N is total number of kind of your data points minus 1, p is the number of predictors. So if I just ignore, let's say this number is something 10 or 50 or 20, right? So this not obviously sum of square error will be less than sum of square total. Let's say this is 0.2. Okay. So sum of square error is 1/5 of sum of square total, right? So if I divide sum of square error divided by sum of square total is 0.2. So that is there. Now what happens as and when I increase p. So initially I had a model which had only, let's say, p as 1. So what will be this ratio, n minus 1 or n, let's say I have 100. I have 100 data points. So what will happen? 100 minus 1 is 99. This is 100 minus 1 minus 1, 98. So 99 divided by 98. But as and when, let's say, I start increasing p. So from 1, 2, 3, now what has happened? P has increased to 9. So I have 9 predictors, 9 independent variables. So in that case, what will happen? N minus 1 is 99, n is 100 because number of data point, number of rows remains same, right? 100 minus 1 is 99. Now what happens? 100 minus 9 minus 1, that is 90. So 99 by 90. Earlier what used to be there? 99 by 98. 99 by 90 is obviously greater than 99 by 98. So what happens? As and when my p increases, this value increases. If this value increases, this factor is also increases because this keeping remaining same, multiplying by only this part, this total multiplication of sum of square error divided by sum of square total and this value whatever it is coming. 1 minus this part also increases. If this part increases, 1 minus whatever that number that decreases, right? So this is the method of penalizing to add. If I'm adding a new predictor, my adjusted R square is actually getting reduced. So anytime we are adding, so haphazardly we should not add a number of predictors, number of independent variables. So that will penalize my R square, which is a adjusted R square. So whenever we talk about multiple regression, we are not looking into R square, we are looking into something called adjusted R square, which is nothing but penalizing any additional independent variables you add to model. So our model should be parsimonious. That means it should be very simple model. Simpler models are the better to explain and better to work on with also, right? So when we look into adjusted R square, we are basically telling our software to look for a simpler model, right? Yeah, yes, Apurva.
Sir, can it be possible that if we remove the independent variables one by one, the R square, adjusted R square, it decreases?
Yes, if your sum of square error is kind of increasing, right? Sometimes what might happen, that might be a very good predictor. If you remove that from your model, your adjusted R square will definitely decrease. So it is not that you have to remove the, so that is where you have to look into the p value. So whenever you are taking out a variable which p value is greater than 5%, right? So you remove those variables. That will have
Yes,
very,
sir.
yeah.
So in the customer data set only, sir, in that only I
Hmm.
was doing the analysis. Over there, I had taken the dependent variable as customer subscription count, and I think I had just the household income and the years, number of years as customer as the two variables I had just taken. So when I removed the gender part and then I took this one, initially when I had taken gender also, the R-square was coming around 0.21. And then I removed the years as customer because its alpha value was very high. It was around 0.82 or something like that. However, the adjusted R-square value, it decreased. It went to 0.17. And but then again, if I added the age variable over there, however, the adjusted R-square value, it increased over there.
Yes, so sometimes you have to like we'll discuss. I think in the next slide only it is that. Let me see. No, here. So this is what like your doubt or what you faced is actually you will face when working with field data. Sometimes you have to take that call, which is important for you. Whether getting a better adjusted R square, which is basically prediction accuracy, you will do away with your whatever the explainability of the model. Maybe the p-value is 0.8 or 0.6 or whatever it is higher than 0.05. Still, we will go ahead and include that to just to build a model with a better prediction or better explainability, better R square value, right? Or when we are just I'm approaching that no, I want my model to work anywhere and I am able to explain that, right? And I'm just looking to p-value, right? In that case, I have to sacrifice my R square. So in your case, it came down to 0.21 to 0.17. You have reduced or you have to compromise that 4% reduction in R square value. But your model will be able to explain it better. Your model will remain valid across wherever you are able to use that. So that is where your compromise has to happen between adjusted R square or R square and your p-value. Sometimes you will face this situation where if you take out a variable, there will be a huge reduction in R square value, though that variable is not like kind of a good do not have a much more explainability because p-value is very high.
So the F value, it increased very well. I think it increased by 4,000 points, but the R square, it fell down by 4%.
So F value shows that the model capacity, like if F value is increasing, that means you are creating a better model, right? So whatever ANOVA table is, when you talk about F value, that is basically the model kind of, it is about the model, how good your model is. R square is about the explainability part of the model, how much prediction you are able to do. Sometimes you have to make that compromise. In academics research, we are not kind of, if I want to publish a paper, I'm much more interested in the explainability part, p-value part. If I go and write a paper where I say that this p-value is 0.8, it is going to be rejected like anything. But in a prediction, when I want to predict something in a corporate and I have two models, one having 0.17, one having 0.21, I might still go with a 0.21 model, though I'm not able to explain why it is happening.
Okay, sir. And sir, also that when I was carrying the linear regression, sir, over there was also an option of categorical variable. So when I added gender there as categorical variable, the output that I got for the least, so over there for it was divided into three factors. It was a female, male, and unidentified. I got the p values for female and male, but I did not get any value. Matlab df value bhi udhar, it was 0, and there was no p value also for the unidentified sector, unidentified group.
Just check that how many count of data in unidentified is there. If unidentified is only 1 or 2, then you might not get the degrees of freedom.
So total data set had 16,019 variables, and out of that U was around, I guess, 50 to 80. Unidentified was 50 to 80. However, it was not being included in the output. So I removed the gender, all three genders.
When you say output means obviously one will be base. So have you like kind of indicated which one is the base reference label?
No, sir.
So it might have, if it is showing female and male, so the unidentified might be the base reference level. So it will not show in your output result. It will not show in your model itself. because that is the base reference.
Okay,
So whenever you use a categorical variable, like I showed that mom's, let's say this one, right?
yes and no.
So here if you
Yes.
say no is not showing, right? Similarly, if I have three labels in a gender, so one will be taken as a reference, so that will not have anything to here, no degrees of freedom, nothing it will show here.
Okay, sir.
Okay, so this is adjusted R square. How to calculate that? Obviously, if I just show you this table, take the sum of square error. Sum of square error is 339.47. That is the residual value divided by sum of square total. This is the total value minus n minus 1. In this particular case, there is 51 data points, which is not given, which was written in previous slide. Then how many predictors? I have only two predictors, female household and whether that person is white or not. So two predictors, 51 minus 1, 51 minus 2 minus 1. So that will give me a value of 0.26. My R square value was 0.29. When I calculate adjusted R square, it is giving me 0.26. Okay, so collinearity. So there are different matrices to understand collinearity. Collinearity is basically whenever you have independent variables which you do not want, whether when there is a high collinearity, there will be always some relationship, linear relationship, right? But when it becomes high, right, and it impacts your model, right? So that is where your multi-collinearity problem comes into picture. So we don't like adding predictors that is associated with each other to the model, because upon time the addition of such variable brings nothing to the table. So in the particular case, if you have taken customer data set, few variables I'll show you by running that BIF and collinearity diagnostics. So those two or three variables are highly correlated, right? So actually when you are creating model, remove that at least one variable from your model. Otherwise, the result what will be getting is will be incorrect one. So how do you measure collinearity? So that is something called variance inflation factor. The reverse of that is tolerance. So variance inflation factor is 1 by tolerance, or other way around, tolerance is 1 by BIF, right? So generally it starts with 1. It can be as high as possible. If something is BIF number is more than 5, sometimes we take 10. If it is more than 5 or more than 10, we take that as a problem in our model, right? Something else is okay. What is the formula? Yes. Whenever again, I'm not going to calculate that. I'll show you how to do it in SAS Studio. Just before that, let me talk about another metrics for understanding multicollinearity. That is something known as collinearity diagnostics. So I'll come to this slide. Let me first show you in the SAS Studio. We will work on that same data set. The data set which I have given you for your class exercise, take that file. So what we'll first do is we'll go and create a or run a regression, right? So let me go to task and utilities. So there are other kind of parameters too, like kind of we'll discuss once we talk about generalized linear model and predictive regression models. So there are other statistics parameters to compare different models, right? So we'll come back to that, but because we only have knowledge about R-square and for a multiple regression adjusted R-square, I'm just selecting adjusted R-square as a model selection parameter. Okay, so let me just run that model. So gender is a classification variable. I want to predict the customer revenue. And I have taken continuous variable age, household, year as customer and customer subscription count, right? If I run this, so this is my final selected model. Hmm. Obviously, other parameters we have not discussed so far. We'll discuss that hopefully by next. Next class, you will have a quiz during your class hours, whatever we are discussing till today, right? So that will be part of your quiz. So average square of errors also we have not discussed. So this becomes my model, right? So, but what I wanted to show, yes. So what I wanted to show is whether some of these independent variables, right, are kind of correlated or not, right? So how will I do that? I'll go and copy this code. So that is one good thing about SAS. Like in your Excel, you have macros, right? You run some analysis, copy that, and create a macro out of it in Excel, right? Same thing, we can do that in SAS. I'll just copy this. Go to here, create a new SAS program. Okay. So what I want to additionally select is this might not run because I have already created a model. Let me check. Classification is gender, continuous is age, So here subscription, okay. Then model edit, add options. Okay. So here. It is taking it. Okay. Okay. Actually, earlier this option was not there. Already it is your outlier analysis also. I can show you here. Okay. So where is my VI? Yeah. So if you look into this variation inflation factor, right? So generally we take 5 or 10, right? How much value is coming for age? If you see age and years as customer, age of that customer and years of that customer have a huge kind of collinearity between them, which is again logically true, right? If the person's once somebody has taken a subscription from you, his age is increasing, also the number of years that person has been your customer, right? So what happens, there is lot of repetition of the explainability, right? So in this particular case, what we have actually have to do, whichever variable has a, and if you see both the variables have very bad kind of p value, right? 0.8560 and here it is 0.7948. Start to remove the highest one, age, create a model, till then also this is like kind of your year as a customer is not a very good predictor, remove that. But the ideal step is if multiple variables are showing multi-collinear property, right? Remove those variables which have highest p-value, right? One by one, then try to see that whether your model is improving, right? So that is the use of VIF for tolerance. Tolerance is nothing but if I divide 1 by VIF, that will give me the tolerance value. Additionally, there is something called collinearity diagnostics, right? So in collinearity diagnostics, what we see, we look into all these variables. So if you see now, all those variables has been shown in your columns, right? You start with the values for any dimension wherever there is a value which is greater than 0.5, right? So what does it mean? There are two variables. So this is nothing but if you have done something called a factor analysis, right? What we take multiple variables and try to create lesser dimension or principal component analysis. It has the same approach. So in this particular case, what is happening? I have all these 6 or 7 different independent variables. I'm trying to see which 2 or 3 variables have a multiple commonality. So how will I find out that? For those variables, I'll look into each dimension, let's say dimension 1, whether there is any commonality between all these variables, right? So I don't find. So how will I find out commonality? Greater than 50% variation. So everything is less than 0.5 here. Similarly for dimension 2 also, I do not find anything. Like that, if I start coming down here, if I find this is where household income is 0.65. So in the same row, I'll try to find out is there any variable, other variable has a value of greater than 0.5. So here like I find for dimension 5, this is 0.65. Household income has a variable variation explanation of 0.65. Whether there are any variable having a similar type of explanation. So I do not find anything, but if I come down for dimension 7, what I find for the age, it is close to 1. Very huge variation of dimension 7 can be explained by age. And in that same row, if I found years as a customer also have a very huge explanation, almost same 0.99873. So that is another way of looking into. If you do not have calculated VIF from the collinearity diagnostics also, by comparing two variables, you'll find out if both of them have higher explanation or higher variation of greater than 0.5. Those two variables are multicollinear or have a huge correlation, right? So same thing what we got from the VIF also I can understand by collinearity factor, collinearity diagnostics. Is this part clear? I hope. Have you gone through collinearity diagnostics earlier on in any course?
No, sir.
Okay. So this is again another because VIF already would have been covered. Anything VIF greater than 5, that 5 or 10 depending upon what you are taking. That means those variables are multicollinear. Or
So in the
yeah.
So in collinearity diagnostics, sir, the each row, these are the data points like 1 to 8.
No. Remember, if you remember what we okay, I have not taken your MR class factor analysis yet. There is something called a factor analysis, right? So factor analysis. So these are 1, 2, 3, 4, 8 are basically by taking those 8 variables, I have created 8 dimensions, 8 different dimensions. So those are
Okay,
not
sir.
data point. And what I'm trying to find out is that if those variables, if I project into those dimensions, whether there are any common variation among those variables. So those 8 variables, I'm trying to project into different dimensions, x-axis, y-axis, z-axis. Similarly, other in 4-axis, 5-axis, I want to project them. So when I'm projecting in the same axis, if I find out that okay, those 2 or 3 variables have a similar type of kind of a variation, then that will give me that yes, these 2 or 3 variables are collinear. These are not 1, 2, 3, 4, 8 are not variables. 1, 2, 3, 4, 8 are dimensions.
Okay, sir.
So this is one thing. What else? I think it is already your okay. What is not here. Cook's T is there, our student is there, student residual is there. Okay, so anyhow, I earlier actually last year when I was using this, there was no, so these options were not there. So actually we used to write code, but it is good that in this particular case already they have included these options. So now we'll discuss something called the outlier analysis. Let it be here. Let me just quickly go through slides. What do I mean by outlier and different type of outliers? Then we'll look into and analyze this result. Okay. Just quickly let me go through the slides. So there are different type of outliers. So outlier, hopefully everybody knows, like if some data is not close enough to your regression line, right? Which is not for the trend, or if I draw a line, right? It is not to the center of gravity or the center of mass of my, or the mean of my data points, right? So basically the idea is, if I have outliers in my data set, out of those 16,019 data point I have, information I have, is there any point or is there any like kind of information which might be wrong, which might be like kind of very random, which has a very huge impact on my regression line, right? So the idea is to find out those outliers which are impacting my regression line and try to remove that and create a model out of it. Sometimes problem happens because data typing error. Let's say Amazon is collecting data in the database wherever they're keeping the data. When you put a SQL query, by mistake, you have not converted some, let's say, age from year to, you have not converted into months, or from month to years, you have not converted, right? So those kind of mistake happens when you are putting a SQL query. So, and now you have extracted data and you are working on that without the knowledge of your mistake. So those, at least what will happen when you are doing this kind of outlier analysis, normal age, let's say for 1,000 or 5,000 customers in number of years. So it is something between 20 to 50 or 60 years. But some customers, it has been taken the months also, right? So by looking into 10,000, 20,000 data set, it is difficult to find out who are those customers or who are those 50 or 60 wrong data point which I have taken for my analysis. So which I can easily find out by carrying out this kind of analysis. So there are three type of definitions of outliers. First two are outliers and high leverage point. So the normal definition of outlier is any data point which is not close to the cloud of point or the center of mass or center of gravity or the mean point, median point of your y variable, right? Your result, your output variable, right? So here the, when we talk about outliers, any result, any output variable, outcome variable, which is not in line with other outcome variables, right? So if I create a plot, if I put a regression line, the ideal regression line will be the line which is covering most of the blue point. But I said no, I have to consider this outlier also. I have still taken that in my data point. So what will happen? My regression line will slightly move towards the outlier. If there are several red dots, so what will happen? Gradually my regression line will move towards that red dot. So then what generally the idea is, create a model using all the data point, create a model removing those outliers and check out whether there is a difference of R-square value. Let's say in this particular case, I'll delete this data point, create my regression model, then I'll include this data point and create my regression model and compare my R-square value, whether there is any significant change in R-square value. If there is a significant change, remove those outliers from your data point, right? So definition of outlier is any outcome or output variable which is not close, which is very far away from your other outcome or output variables, right? Then there is something called high leverage point. High leverage point is something which is according to your regression line, which is according to your like kind of trend line, but it has a significantly different independent value, independent variable value, right? So just look into this scatter plot and see the difference. In this particular case, what has happened? In the first left side of the left part of the scatter plot, for the similar x values, right? I have one outlier. If I look into this x value of 4, I have a value which is in line with my regression line. If I put a regression line, it will be upward slope line starting from here, from the corner to the other corner, right? So if I look into the value of x at 4, I have blue dots and there is a outlier which is a red dot, right? So there is a difference in your outcome value. There is a difference in your y value, right? Which I want to predict. Here what happens? You have particular outcome variable, or let's say x is equal to 14. For all other outcome variables, your range of x is between, let's say x is something age and y is income, right? Or x is some, let's say your quiz score, and y is your final score. X is a particular quiz score out of 0 to 20, and y is your final score, right? So if you see, the range of almost all the variables is between 0 to 10, right? But there is one value for x is equal to 14, and obviously there is a separate y value. So how does this red dot comes? There is a, for those outcome variables or for those output variables which is beyond the normal range of your explanatory or independent variable. So that is a high leverage part. So again, repeating the difference between these two charts. In the first chart, we are looking into the y value or the value of your dependent variable. In the right side of chart, we are looking into those values which have a significantly different independent variable. Independent variable is x, right? For all the y values, right, your x is ranging from 0 to maximum 10, but there is only one data set, one data point which have a significantly different x value. X is the independent variable. So for those outcome variables which have a significantly different x value or the independent variable value, so those are known as high leverage point, right? So is it clear the difference between outliers and high leverage point?
Yes, sir.
Okay. Then influential points, right? So those, whether it is a high leverage point or your outliers, which significant changes your regression line, regression equation, right? So those are known as influential point, right? Not all the outliers, not all the high leverage point significantly have an impact on your regression line, but those outliers or those high leverage point which have a significant impact on your uh, a regression equation, that is a influential point. So generally, as you know, that more the temperature, more the kind of that star signs, right? The intensity of the light is more, right? So they have taken 47 stars, and what I have taken log of light intensity, the amount of light they are emitting, and the temperature. The idea of the normal theory of physics is more the temperature, more the intensity of light. But the problem is there are few points. So these 4 points are influencing your regression line. If I create a regression line, including all the 47 stars, their light intensity and their temperature, I'll have this green line. This regression line almost what will be the equation? Around 5.4 minus 0.1 or 0.2 some log of temperature. So if I write a equation for this line, it will be something like log of light intensity is equal to 5.4 minus, because it is a negative flow, maybe 0.1 or 0.2 of log of temperature, right? So this is the regression line if I use my all the outliers. If I do not consider all these 4 outliers and I take that data of all these 43 points, excluding all those outliers, I'll have some regression line which will be almost kind of a upward moving curve, right? Here what is happening? It is a downward moving curve, right? So ideally what should happen? As your temperature increases, your light intensity should increase. But in your green dotted line, what is happening? As your temperature is increasing, actually light intensity is decreasing, which is actually opposite to the logic of physics, right? Ideally what should happen? Your temperature of the star is increasing, light intensity is increasing. So if I remove that outlier, I'm getting a better explainable or better regression line, right? So if you see these outliers which are influencing my regression line, so those are known as influential point, right? Not outliers, not all outliers, not all high leverage point influence your regression line. Out of all the outliers, high leverage point, those points which have an impact on your regression equation, those are known as influential point. Clear?
Yes, sir.
So how do you find outliers? So outliers, basically there are many statistics. Two statistics or mostly used statistics are studentized residuals. So the formula or the equation is student in the SAS studio, and there is something called deleted studentized residuals, R student. So the difference between these two is studentized residuals is the basically the like kind of a standardized version of our regular residuals. If I divide by the mean square of error, deleted studentized residual is if I delete the observation. Let's say if I'm telling that this is the outlier, if I delete that observation and I create a equation, a regression equation, and now I'm trying to find the distance between new line, new regression equation, and the observation which I have deleted. So that is why it is known as deleted studentized residual. Studentized residual is the whatever residual you calculate. Residual is nothing but your actual data minus predicted data. You divide by mean square of error, that will give you a studentized residual. Deleted studentized residual is if I remove that observation, if I say that okay, this is outlier and I remove that observation and create a equation, right? Equation might be slightly different. And now what I do, I try to find the distance between my new equation, new line, and the data point which I have deleted. That will be deleted studentized residual. Levi's okay, outliers are data point which response y doesn't follow the general trend of. So outliers are basically outcome variables or output variables are different than the other output variables. Leverage point where you have extreme predictor x values, right? So there is something called H matrix, hat matrix or H, the cutoff value. So which are the point I should consider as my leverage point? The formula is 2 multiplied by k plus 1 divided by n, right? So in the like kind of this customer data set, I have how many? 5 or 6 independent variables. Let's say I have 5 independent variables, right? So what will be the formula? 2 multiplied by 5 plus 1, 2 multiplied by how much? 6, 12 divided by n. N is very high. N is around 16,000. So 6 divided by 16,000. Whatever it is coming as 0.00 maybe 16 or something like that, it will come 0.00016. So those point for each of the point for each of those 16,000 observations, I'll find hat matrix or H value for those point which have greater than this cutoff value, right? I'll remove that. I'll remove that and try to see that whether those are high leverage point. So those point who have a H matrix or H value greater than this value 2 multiplied by k plus 1 divided by n. K is the number of independent variables. N is number of samples or number of data points. So influential point. So generally we measure by Cook's distance. The cutoff value of Cook's distance is very simple 4 by n. So if I have 16,000 data sets, 16,000 data points, 16,019, 4 divided by 16,019 will be close to 0.00025, right? So that is my cutoff value for influential point. So those for each of the data point, I'll calculate Cook's D for those observations for those data point which have Cook's T greater than 0.00025, right? I will kind of not consider that because those are the influential point. I'll not consider them for my whatever kind of analysis I'm going to carry out, right? So this is the basic three outlier analysis statistics. Again, there are some D fits, DF fits, but these are the basic three which we consider for our outlier analysis. Any questions or any doubt?
Yes, sir, I have a question. So
Yeah.
Studentized residuals and the deleted studentized residuals, sir, do we just use it on outliers, or can we use it on leverage and influential points also?
Studentized residual or deleted studentized residuals for the outliers, right? For high leverage point, it is the value of x-axis, value of the dependent variable.
Yes, sir, because
Yeah,
yes.
go on.
So because if we make a cluster of outliers, that can also become the influential points.
Cluster of outliers.
Yes, sir.
What
So
do you mean by that?
So like in that you had shown that outliers, you had shown that there was one red dot at 0.4.
Correct.
So if I don't have 1 point over there, I just have more than one, I get 10 points over there. From there will be points from 3 to
Yes,
5.
so the normal kind of standard is if 10% of data points are clustering, you should not remove that. So let's say I have 16,000 data sets. So when I say I have to remove those observations, but let's say I have to remove 1,000 or 1,600 observations, I should not do that. So the limit of removing those cluster of point is up to 10%. If it is something more than 10%, I should not remove that because that will influence my regression line, and that is okay. I should not remove any or every influential point. So to answer your question, if let's say I have different cluster of data, right? So
Yes,
and some cluster of outliers is almost more than 10% of your data set. That means if I have 16,000 data points, there is few clusters which are, but let's say some clusters are that 200 data point, 300 data point. By removing that, I can look into my model. But let's say there is some clusters which are 2000 data points. I should not remove all those 2000 points because that will like kind of negatively influence my model.
and sir, can I have a combination of all these three in my data? The influential points, the leverage points, and outliers.
So ideally, we look into mostly influential point because we are interested in those either outliers or high leverage point which are influencing my model. Then only if
Yes,
my
sir.
model is not improving, then only I'll look into the outlier and high leverage point. But my main focus is there any influential point? Influential point means any outlier or high leverage point which are influencing my regression equation. So first I look into the Cook's T. So any point which are out of the 16,000 which has more than 0.00, that 4 by n. How much 4 by n is coming? I think that will be 0.00025. For those observations, you remove that from your data set. Do not consider for your equation. Then see that whether your model is improving or not. Then
Okay,
also if
sir.
model is not improving, then come back and see that whether there is something else you can do away with, removing some high leverage point and some like your outliers. But first step is
Okay,
to
sir.
remove the influential part.
Yes, sir.
Okay. So this is, if you see here, almost it is already given. So these are your studentized residual. It is giving us how far it is from the mean data point, right? So if you see here, minus 0.518. If you see the star mark is here, from the mean it is towards the negative 0.727. From the mean it is towards the positive side 0.727. So again, like if your influential point analysis did not work and you want to remove some of the outliers, you can look into those outliers which are 2 standard deviation, left side of 2 standard deviation, right side from your all the data point, right? From the mean value, if some values are there, minus 2 standard deviation or plus 2 standard deviation, right? You can look into removing those values, right? So is there something? So here if you see there is a value 46, 14.991. So this student is, so it is a very big, and what is the Cook's D? Cook's D also if you see it is 0.026. So this is a very big influential point. Ideally I should not consider, I should remove this from my data set and work on that. Like that also there will be, so 2.090. So if you see in this particular case, Cook's t is 0.000. That means it is not an influential point, but it is a significant, it looks like a significant outlier, right? So now what happens by removing, first I'll remove those point which have a very highly influential point by looking into only Cook's t. Then only, and I, let's say out of 16,000 data set, 500 data points are removed. Now I'll work on those 15,500 data. Still my model is not improved, then only I'll come back and look into other data which are outliers or high leverage point. High leverage point is H matrix, where is H? At diagnostics or H, right? So that the formula is 2 multiplied by k plus 1 by n. So any H value which is greater than that, remove that highly leveraged point, right? But first our focus is on to remove the influential point. Is this part clear or any doubt?
No, sir, clear.
Okay, so quickly, what else is left? Okay, so quickly just let me talk you through a few of the data transformations. So basically the idea is how you interpret the data transformation, right? So there is something called, if I am doing this log transformations, right? So there are many ways to do log transformation. Let's say I have an equation called y is equal to a plus bx. So one way to carry out log transformation is that I will transform my dependent variable. That means I will transform y. So rather than y, I'll take log y. So let's say I have income data. Income data is dependent on your age. So income data, rather than taking as income data as such, I'll make a transformation of log income, right? So that is one way to do it. Second way is obviously keep y as same, but make a transformation of your independent variables. That means y will become a plus b log x, right? So that is another way of transformation. Third way is obviously do the logarithmic transformation for both the variables y and x. Log y is equal to a plus log b log x, right? So those three specific transformations have certain name. First one is log label regression. So from the name, if you see, when I say log hyphen label regression, so the right side part is remaining label. There is no change. Left side, what will be there? Your left side of the equation is y, your dependent variable. There is a logarithm transformation for that. So the name is log hyphen label regression. Log label regression means I am making a logarithmic transformation for my y, that is my dependent variable, whereas my independent variable remains same. So in this particular case, let's say y is equal to some equation I put, that is 5 plus 0.03x. I made a transformation. I made a logarithmic transformation for my y. So my new equation will be log y is equal to 5 plus 0.03x, right? But how to interpret that? In this particular case, if I had not made any transformation, the simple interpretation is for any unit change in x, y will change by 0.03, right? If I had kept it like this. But when I'm making a transformation, right? So what I'll do, I'll put logarithm y is equal to 5 plus 0.03x. So the x2, so okay, log y2 is equal to 5 plus 0.03 x2. Log y1 is equal to 5 plus 0.03 x1. I subtract log y2 minus log y1. So simplify the equation. So log or logarithm natural scale, logarithm y2 divided by y1 equal to 0.03 multiplied by x2 minus x1. So how to end if I make exponential transformation? My final equation is y2 divided by y1 is equal to 1.03 to the power x2 minus x1. So how to interpret this? For any one unit transformation in x, let's say x2 minus x1 is 1. Your y2, your value of y is changing by 3%. So if let's say x2 minus x1 is 1, what happens? y2 divided by y1 will become 1.03. That means whatever y1 was there, if I change x1 by 1 unit, my y2 will become 1.03 y1, right? So if you increase x by 10 unit, what will happen? 1.03 to the power 10, that will give me 1.34. That means my y value is changing by 34%, right? So the only, like I said, whenever you get into little bit complex model, it becomes difficult to explain the model. In this particular case, if I have not made any transformation, it is very simple to explain. For each unit of x, keeping everything same, y will increase by each unit change in x, y will change by 0.03. But when I'm just making a simple transformation of y, the interpretation will happen in this way. For each unit change in x, y is changing by, obviously depending upon the equation, right? In this particular case, so it will be 1 point whatever the your exponent value or the coefficient value, it is 0.03, that's why it is 1.0. If it was something else, it will be, let's say it was 0.5, it would have been 1.5, right? A label log regression, as the name suggests, your left side remains same. That means your y value remains same. I'm making a transformation of the dependent variable. Sorry, independent variable, right? That is the right side. Same equation, 5 plus 0.03x. Now I have made the change, transformation. And when I simplify this, y2 minus y1 will become 0.03 ln to the power x2 divided by x1. For each unit change in x, right, my y value is changing into 0.03 natural logarithm of whatever value, right? So if let's say x increases by 10%, that means x2 is 1.1 x1, right? So this will become 0.03 multiplied by logarithm of 1.1, 0.003, right? So if a 10% increase in x, y is changing by only 0.3%. X increases 50%, again you can calculate it is only 1.2%, right? So the point is transforming one variable or the both the variables, right? Interpretation step by step becomes difficult. Log regression is transformation is happening both for dependent variable and independent variable. So again, I do the transformation and take different y2, different y1 and try to simplify the equation. So y2 divided by y1 will become x2 divided by x1 to the power 0.03. 0.03 is coming from here. So how to interpret that? If for each unit increase in x, so x2 by x1, whatever the value is coming, let's say x increases by 10%, x2 becomes 1.1 x1. So 1.1 x1 divided by x1, that is 1.1 to the power 0.03, right? So that is 1.003. So if your x changes by 10%, your y is actually changing by 0.3%, almost equal to what we saw in the previous slide. If your x changes by 20%, y is changing by 1.2 to the power 0.003, that is 1.005. That is basically 5%. So the point is, whenever like you are making a transformation, right? Any kind of, I just showed you the log transformation. Just imagine the scenario when you are doing this inverse transformation, actually easy. Square root transformation, right? Or any kind of polynomial transformation. It becomes very difficult to explain the model, right? So that should be your last step. Let's say your model is still not, let's say this customer data set model is still not giving good R-square or adjusted R-square. Then looking into the scatter plot, you can look into like what kind of different kind of transformations you might need to do, right? Not necessarily always transformation is required. In case it is required, that should be your last step, right? So that is about your model selection steps. Carry out preliminary analysis, look into scatter plot, look into different independent dependent variable. Collinearity detection, if there are certain independent variables which are collinear, remove that, create a model out of it, then look into the outliers, influential observations. Those outliers are high leverage points which are influencing your model. Look into them, revise your model, then only prepare your final model and send it for your production level testing, right? So these are the few basic things which you have to do before you finalize your model. collinearity detection and outlier analysis. In case it is required, you might have to revise your model to carry out certain log transformation or square root transformation. But again, I will advise against them because explaining that again becomes difficult. Unless it is very much required, do not get into that. So that completes your today's discussion. Any last questions before we close? Okay, so if not, that's all for today. Please be ready for quiz. I'll share the slide and I'll share the kind of videos. Please prepare for that. There will be 10 marks quiz, 10 minutes, 10 marks quiz in the next class during the class hours. Okay. Chalo, take care.
Sir, the
Yeah.
first assignment, sir, I have submitted today, sir. So if you could go through it. So it's a bit lengthy.
Yeah, I'm not still evaluated that. Let me go through it and we can discuss that in the next class.
And sir, the test will have all the theoretical based questions.
Mostly theory, maybe one or two calculation, but mostly
Sir,
theory.
analysis also.
Yes. So analysis means I might keep a like output and you have to look into it and like whatever we discussed today, something similar to that.
Okay, sir. Thank you, sir.
Yeah.